Actually a short circuit, what short circuit is defined as actually a path of low resistance. Okay, it is a path of low resistance in an electrical circuit which passes an abnormally high amount of current through it. Okay, now how we can obtain a short circuit in an electrical circuit is by just directly connecting the two ends of 2 points on an electrical circuit by a connecting wires. Okay, so if we directly connect the two ends by a connecting wire, we can obtain a short circuit. Okay. Generally, short circuit is not desired in the circuit because it can damage the power supply. Now, as we can see in this example, suppose that I have a lamp. Okay, it is connected to a source of EMF E. Okay, now across the lamp, I have parallelly I have connected a switch. Okay, K. Okay, now when the switch is open, the current will flow through the lamp and the lamp will glow. Okay, now but imagine what will happen if the switch is now closed. Okay, when we are switching, when the switch is closed, what we are doing is we are giving the charges to flow to an alternate path. Okay, the charges won't flow through this path because now we have connected a low resistance path across the length. Okay, so the charges have the property to travel across the low resistance path. So the entire charge or the entire current will flow across the short circuit path. Okay, that is when the key is closed. Okay, the entire amount of current will be flowing across this path. Okay, so no current will flow across the lamp, so the lamp won't glow. But this has an adverse effect on the supply because the entire current will be or the entire current will flow again back to the power supply, which can damage the circuit, which can damage the power supply. So this circuit, that is an short circuit, in this case it is an undesirable concept. But this concept of short circuit we can use to reduce the combinations of resistors, that is to determine the resistance. That would be helpful in order to determine the equivalent combination of resistance. Okay, as we'll see in our next example for a symmetrical structure. Okay, so from now just we need to remember one thing, that a short circuit is a path of low resistance. Okay, and it allows the entire current to flow through it. Okay, so for a short circuit path, we'll be having the maximum current passing through it. Okay. Now let us consider a symmetrical structure. Okay, we need to determine the equivalent resistance for this symmetrical structure between the two endpoints. Okay, so in this problem, we have to determine the equivalent resistance between the points P and Q. Okay. Now, as we can see from here that this structure, this circuit is symmetrical. Okay. Now we can consider this as symmetrical about this perpendicular axis. Okay. So this is the axis through which the circuit is perpendicular. Now, as that is symmetrical. Now, as we have seen earlier, that for a symmetrical structure, we can reduce the structure into half. Okay, and find the equivalent combination or the equivalent resistance for half of the structure. Now, why we do this thing is because when the structure is symmetrical, then across the perpendicular axis, the potential across each of the points will be similar. That means these three nodes, okay, they have the same potential. Okay, so if they have the same potential, there won't be any current flowing across this branch. So what we can do is we can replace it by, okay, since they are of equal potential, we can replace it by a short circuit or a conductor. Okay, so after doing this, okay, since no current flows through this path because the potential difference at all these points are similar, so these resistors of values 2R will become redundant. Okay, no current is flowing, so there is no point of connecting these two resistors in this circuit. Okay, so what we can do is we can eliminate these two resistors. Okay, and also what we can do is we can remove the other half of the structure because the structure is symmetrical. Okay. At the end, we'll be multiplying the results by 2. Okay, since these two are connected in series. Okay. So what we have done is we have introduced a short circuit, okay, across the perpendicular axis, that is the symmetrical axis. Okay, and across the symmetrical axis, since the potential was similar, okay, so the resistance which were present on this perpendicular axis, that is on the symmetrical axis, will be redundant. Okay, so we have removed it. Okay, so let us assume that this point is something. Suppose this is A. Okay, so now here what we are required is we need to find the resistance between the points P and A. Now if we'll see carefully, what we can see here is that all these three resistors, okay, they have their endpoints in common. Okay, so since their endpoints are in common, okay, what we know is that since the endpoints are in common, they are connected in parallel to each other. Okay, so the equivalent resistance between the points P and A, okay, the equivalent combination between the points P and A, it would be 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay. In this case, the value of R1 is 2R, the value of R2 is small r, and the value of R3 is 2R. Okay, so here we will be getting 1 by 2R plus 1 by small r, 1 by 2 times of R. This is equivalent to 1 by R equivalent. Okay, so after solving this, we will be getting the value of this as 1 by R plus 1 by R. Okay, that is equal to 1 by R equivalent. Therefore, R equivalent is R upon R plus R. Okay, so this is the value of the equivalent resistance between the points P and A. Okay, but what we require is to find the value of the equivalent resistance between the points P and Q. Now, since the structure was symmetrical, okay, so what we can do is we can connect the same value of the resistance, okay, and the other half. Okay, so what we'll be left with is a circuit containing two resistors in series. Okay, we had the point P. Okay, between point P and A, okay, we have a resistor whose value is this. Okay, and since the structure was symmetrical, so again between point A and Q, we'll be having the same value of resistor. Okay, and these two resistors are now connected in series. Okay, since the same current is flowing through both the resistors. Okay, so the equivalent resistance between the points P and Q, now it would be the addition of these two resistors since they are connected in series. Okay, so the value of the actual resistance is. So from here, what we can see is that if we want to solve any symmetrical structure, we can introduce a short circuit path across it, okay, and we can remove all those resistance which